All right, today we're looking at our next set of word problem style problems, and this is optimization. This uses the ideas we set up in curve sketching to find the maximum or minimum in a word problem. So let's look at the situation. Apple Orchard has 20 trees right now, and the average yield is 300 per tree. For each additional tree planted per acre, the average yield is reduced by 10 apples. How many trees per acre will maximize the crop of apples? Well, our crop is going to be the number of trees times the yield. Well, as we're standing right now, that's going to be 20 times 300. But that's not what we're looking at. We're adding some trees. So plus, can't erase, there we go. Plus t. So we're adding some trees to the field. And every time we do, our yield reduces by some amount. The yield is going to be 300 minus 10t. There we go. Minus 10t, not just t. So our yield is reducing by 10 per tree. Okay, so every tree we add will reduce this by 10. So we can actually set up an equation here that we can solve. We could do product rule if we wanted, but we're looking for the derivative. We're looking for maximizing the number of trees. What t value will make us have the maximum, or not maximizing the number of trees, maximizing the crop. So let's distribute this. We have 6 and then 3 zeros minus 200t plus 300t minus 10t squared. So that's 6,000 plus 100t minus 10t squared. And we want to find where this is. We want to maximize this, so we need to take the derivative of it. So dc, and this is not a related rate. It's not with respect to time. We're looking at the change in crop with respect to t, which is our number of trees. The change in crop with respect to our trees. So we're really just taking the derivative of t normally. So that's going to be 0. That's going to be 100 minus 20t. And then we're going to set it equal to 0 and solve. So 0 equals 100 minus 20t. Add the 20, divide by 100. We get, add the 20, divide by 20. Add the 20t, divide by 20. T is equal to 5 trees. Now, let's look at what the question was asking, because this looked like an answer. It's 5 trees, but it says how many trees per acre. This represents the number of trees we're adding. The trees per acre is this equation we had right here. So it's 25 trees per acre. We'll maximize that crop. Okay? Now, most of these are designed in a way so even if you have multiple answers at the end, there's only one that makes sense contextually, and you'll see it as you work different problems. All right, here's the next one. You're trying to make a metal canister with a volume of 200 cubic centimeters. The thicker the metal at the top and bottom costs, or the thicker metal at the top and bottom cost 8 cents per square centimeter, while the sides cost 3 cents per square centimeter. Find the height and radius of a cylinder that maximizes the cost of producing the can. So we know that the volume has to be 200. The thing with these is, unlike with related rates, because we're just taking the derivative not implicitly, you have to have only one variable in your equation. So let's create the equation that we're maximizing. Our cost equation is what we want to maximize. So it's a cylinder. Let's think cylinder here. It said the top and bottom, this thicker material at the top and bottom, are going to be more expensive. So the cost of them is going to be 8 cents per square centimeters. Well, the square centimeters is just the area of these shapes on top and bottom. So the area of a circle is pi r squared. We have two tops and bottoms, so two circles, top and bottom, so 2 times pi r squared, then times the cost to do this. So times 8 cents, really it should be 0.08. We'll do 0.08 to make this easier. That's really not giving me much room to work with. There we go. So that's the cost for the top and bottom. Then it says the sides cost 3 cents per square centimeter. Now, if we're thinking about a cylinder, if we were to break this open and roll it out, this creates a rectangle. So we're looking for the area of that rectangle. Well, the top or the side here, this is the height of the rectangle. That's just going to be h. This top, it forms, if we roll that back up, it rolls into a circle there. Okay, it's rolling up, and if you were in class, I'd show you like a dollar bill, rolling it up and creating a circle. That rectangle turns into a circle at the top and bottom. So this side right here is just the circumference of the top or bottom, which is 2 pi r there. So our area of that face of this shape is 2 pi r h times, and then the cost to produce that side, which is 3 centimeters, or 3 cents per square centimeter. So 0.03. All right. And now this is the equation we want to maximize. So let's go ahead and rewrite this. So 0.16 pi r squared plus 0.06 pi r h. And notice this equation is close to being able to take the derivative of, but we have the h here, or the r, whichever one you don't like. Either way, we got to get rid of one of them. We can't keep both of them in there. So, actually, we're trying to minimize the cost. I think I said maximize earlier. We're trying to minimize the cost. So we need to find a way to replace the h. Well, that's where the volume comes in. We know this can needs to be 200 centimeters cubed. So we know 200 has to equal the volume of this cylinder. The volume of a cylinder is 2 or pi r squared h. Well, now we have the information to simplify and solve for a variable. We can say h is equal to 200 over pi r squared, and we can plug that in for h here. Okay, so the pi's are going to cancel. The r is going to simplify down to an r on bottom. And so we end up with 2.16 pi r squared plus, and then 12 with it, so 12 over r, if I did that correctly. Yeah, 12 over r. All right. Really, we could say, if we want to make this easier, it's 12r to the negative 1. And that's because we need to take the derivative. So dc over dr, the cost with respect to the radius, is going to be 0.32 pi r plus, and then, well, really this should be minus 12r to the negative 2. And just like any other optimization problem, we need to get a common denominator. So this is going to be 0.32 pi r cubed minus 12 over r squared. And we end up being able to find two places where this could be maximized. R ends up equaling the cube root of 12 over 0.32 pi, or it equals 0. Now, which of these makes sense in the context of the problem? This looks like an ugly number, but this one makes sense. If we had a radius of 0, sure, that would minimize the cost of the can because there would be no can to produce. So this is going to be the r we use. So there's our r, and this would be a calculator problem. You plug it in the calculator, and then we could plug it back in over here to find the h. So we could get both the r and the h. All right, so if you're in class, you have some worksheet to do. If you have any questions, let me know. Otherwise, see y'all next time.